Okay, so everybody from the Chinese physics community, so good evening. Welcome you to participate in the open seminar in Frontier of Nuclear Physics. I am Miguel Marqués from Fudan University. Today, I'm very happy to chair the 54th seminar of this series. The present seminar will be given by Professor Miguel Marqués from CNRS LPC Laboratory, University of Caen, France. He is one of very active scientists in nuclear physics experiment, especially for the nuclear action and nuclear correlation in the worldwide. This seminar series is hosted by Fudan University, as well as Shanghai Research Center for Theoretical Nuclear Physics, National Science Foundation of China. The seminar is also co-organized by the Journal of the Nuclear Science and Techniques, as also as its Chinese edition, Nuclear Techniques. The seminar is open for public community of nuclear physics in China. This seminar is also live show by the co-share.com by USTC. Professor Marqués will give a talk, multi-neutron emission. So I think this topic is very timely and interesting, since there are a lot of new progress on this multi-nuclear correlation. Before the talk, I would like to make a brief introduction to Professor Marqués. Professor Marqués is CNRS Senior Scientist at LPC Caen, France. In 1994, he got a PhD on Bose-Einstein correlation between hard photon from the GANIL-Caen and IFIC-Valencia. From 1995, he is a member of the exotic nuclear group at LPC, involved in the study of the correlation and the research on new phenomena in very neutron-rich light nuclei at GANIL. With the explosion of the new techniques such as neutron interferometry, proton radioactive capture, beta delay neutron emission, observation of the multi-neutron resonance, or the detection of the neutron clusters. From the 2012, he performed the experimental program using the very intense and very neutron-rich RIKEN beams. Some examples are the study of the oxygen-28 and the hydrogen-7. The explosion of new phenomena like Efimov state in the volume-19 and dineutron emission in barium-16. The measurements of the very large scattering lengths like the volume neutron 1 and the construction of the second half of the NEBULA neutron L for the next generation experiments. So he will give a talk for the multi-neutron this evening, and let's welcome Professor Marqués. So, Marqués.
Thank you very much, Professor Ma.
Recording in progress.
So thank you for your kind invitation, and so I hope that in the near future I will be able to visit physically your university. But just today, let me show you some overview of the research we do on multineutrons. So you see that I added a word on the title. So detection of multineutron emission. And so the physics case is the multineutron systems. So this is the main subject I will talk about. And then there are two keywords here in this title, in this final title. One of them is emission, and you will see why. why are we interested in the emission of multineutrons? And the other one I added at the last moment is detection, because I will talk about the detection of this phenomenon and not about the theory. And first, before I go to my plan, for those that are not aware, so as Professor Ma said, this is very timely research, because last year there was a confirmation of a 4-neutron signal. And the first observation of this 4-neutron signal was at GANIL by our team in 2002, where we saw that in the breakup of beryllium-14, some events were consistent with, so this here is the proton recoil in our neutron detectors compared to the neutron energy. So this should be at most 1. So this should be confined in this area. But we observed some events that were consistent with a very big proton recoil, and this could be explained by the arrival of a neutron cluster and not of a single neutron. So this was in 2002. The signal was weak, about 2.5 sigma. And then in 2016, it was a result from RIKEN, Kisamori work with Shimura-san, where they observed by missing mass some events close to threshold at about 0.8 MeV. So we're consistent with a 4-neutron resonance at almost 5 sigma. So for all this period and before, I wrote in 2021 a review paper. You have the reference here, where I summarized all these experiments, and Carbonell made a summary of the theory. And finally, last year, it was our collaboration published in Nature, this very strong 4-neutron signal. So if you have a look at the spectrum, it's very similar to Kisamori one. You have a signal at threshold and then some broad component. But here now the signal is very significant. So this was the energy, much more than 5 sigma. And the problem, if we can call it a problem, is that these experiments were done by missing mass. So here you have the 4-neutron energy, but the neutrons are not measured. So they reconstruct, so you have something like this. You have charged particles, you have neutrons, and then you reconstruct the neutron as a single object from the mirror image, so by energy and momentum conservation. So what you get is an average, a global view of the neutrons that you don't detect. And what you see here is that the energy is about 2.5 MeV. And this year, Lazauskas and collaborators published an alternative explanation to this signal here. So instead of a 4-neutron resonance, they said that this could be just the reflection of dineutron correlations in the wave function of helium-8, which is the beam nucleus. So, but of course, in order to see, do we have a 4-neutron resonance, or do we have just the manifestation of a structure in the beam that we use? For this, we need to measure the correlations, and so it means that we need to measure the neutrons. So this is what I will talk to you about, the interest in measuring the neutrons. And another issue is that, as Lazauskas suggests here, he suggests that signals that we see may be the result of the probe that we use and not on the properties of the system. So this is why I will concentrate on the emission of multineutrons and not on the reaction to build these systems. So now I come to my plan. I will show 3 examples. The first one, so I said a spontaneous emission of multineutrons, so it is emission. So we are going to form a system, and we are going to form a system which is unbound. So it will spontaneously emit the neutrons, and we will be free of reaction mechanism. In the first case, it will be the 2-neutron case for beryllium-16. So this is part of the PhD of Belén Monteagudo. And the question that we will ask here is this beryllium-16 decay a two-body decay, as it was claimed some years ago? Do we have really a dineutron decay? And what is the experimental signature of this correlation between two neutrons? Then we will see the 3-neutron case, this part of the PhD of Cyril Lenant, in which we will try to build an excited state of helium-7 that will decay into helium-4 and 3 neutrons. And here we will see if we can detect 3-neutron emission and what would be the signature in this decay of a trineutron. And finally, also part of Cyril's PhD, the 4-neutron case. So in this case, the example will be hydrogen-7 that will decay into hydrogen-3, the triton, and 4 neutrons. And in this case, there will be two questions. First, where is the ground state of hydrogen-7 if we measure the 5 particles? And what would be the signature of a tetraneutron in the decay of hydrogen-7? So these are the three. I hope I will make the 3 examples in a bit less than 1 hour time. And we will start with the 2-neutron case. So beryllium-16. In 2012, there was a claim from the MSU group saying that they had observed dineutron decay for the first time. The idea was try to create a system in which the system is above the 2-neutron separation energy, like oxygen-26 or beryllium-16, and see if, as some people predicted, we can see a two-body decay. So the emission of one single object that decays into 2 neutrons. So this was published, and first observation, a lot of noise of this observation back in 2012, saying dineutron decay. We wrote a comment. If you go to the page, you will see that very far below is a comment saying that the observation could be explained without a dineutron hypothesis, but this was the impact in the media was very strong. So in many places you could read that the dineutron decay had been identified. That was a new type of decay, the emission of a neutron pair, and the neutron pair emitted as a single unit. So we tried to repeat this experiment at RIKEN in better conditions to see if this was true. And this, I will use this slide for those that are not familiar with RIKEN, to show you where we work. So we work in the Samurai area at RIKEN. We start with a primary beam. So in the case of beryllium-16, this is the primary beam accelerator, the superconducting ring cyclotron. We are going to break at about 0.6 velocity of light. We are going to break this calcium-48 beam and try to make something exotic, in this case boron-17. So we have to remove all these protons and neutrons from the beam. And once we have created this boron-17, which is a 2-neutron halo, we conduct it to the Samurai area, and in this area we remove plus proton. And then we make beryllium-16 that will decay into 2 neutrons and beryllium-14. So this is the basic principle of our experiment. You have a primary beam, you create something exotic, and then you do a reaction and try to detect something even more exotic. In this case, what do we need to detect this system we created? In the case of beryllium-16, we are going to detect 2 neutrons and 1 beryllium-14. So the next thing is, do they come from a single object? So if we want to create beryllium-16, as I said, we need the easiest thing is take boron-17 and remove 1 proton. And the easiest way to remove a proton is using another proton. So we remove this proton, we detect the other proton, and we have the complete kinematics. In order to do this, this is what the setup at the Samurai room. So we detect the 2 protons around the target. We detect beryllium-14 in after the dipole in the focal plane of Samurai. And the neutrons will go through the magnetic field and will be detected in the neutron walls here, nebula. And then how do we know that we created beryllium-16? So if we have the complete kinematics, we take a picture of the system by reconstructing the static properties. So what is the energy, what is the width, spin and parity. And then if in addition we measure the correlations of in the decay, we can, it's like taking a video of the decay. So we have a picture, what we created, and then we have the video of how it decayed. Is it sequential? Is it direct? Do we have neutron-neutron correlations? So this is the principle of detection that we use. This was the result that was published in 2012. So the picture that they took of beryllium-16 was this one, something very broad at about 1 MeV. And the movie they claimed they have observed was a 2-neutron signal at low energies. And this is the spectrum that we measured. So this is from the thesis of the PhD of Belén Montagudo. So here you have the same scale from 0 to 5 MeV, and then we measure up to 10 MeV, and you see that we don't observe the same thing. So we have better acceptance, better resolution, and we observe clearly a ground state lower in energy and an excited state higher in energy. These were fitted. So here you have the ground state that should be a 0 plus as an even system, and the 2 plus, the first excited state. So this is our level scheme, 0.84 MeV ground state, 2.15 2 plus state, and then we measure the decay, and we observed, here you have one state in beryllium-15 at 1.8 MeV. So we were able to distinguish these 2 states and to measure the 2 decays. This decay can be only direct, but this decay could be also sequential, and we observed that it is also direct. And then we wanted to compare this with more sophisticated models than were used in the previous work from MSU. And for this, we use this formalism from Casal, which is in some sense similar to Professor Wang that he used at first for proton-proton case, and is also extending to neutron-neutron case. So here you have the calculations from Casal for the 0 plus state and for the 2 plus state. And here you have the neutron-neutron distance, and here you have the distance of the 2 neutrons with respect to beryllium-14. And you see that for the ground state, you have this dominant configuration of 2 neutrons that are close. In the 2 plus case, you have something very diffuse. So it's not so compact. And then, as also Professor Wang calculated in the proton case, Casal wanted to work with us to calculate the decay of this wave function. So here you have Dalit plots of the 2 neutron decay. So this is the neutron-neutron relative. So you have the 3 particles in the final state, beryllium for a fragment and 2 neutrons. Here you have the neutron-neutron energy normalized to the total energy. And here you have the fragment neutron energy also normalized to the total energy. So between 0 and 1. This is the 2 plus resonance of beryllium-14. So beryllium-12 plus 2 neutrons. And you see that the decay follows phase space. So if the Dalit plot corresponds to phase space, you have something flat. And these are the same plots for the beryllium-16 ground state and first excited state. So you see that for both of them, you have at low neutron-neutron energy, you have an increase in the probability for the 0 plus and even more for the 2 plus. And trying to analyze this in a more quantitative way. So here I plot the projections onto the neutron-neutron energy of these 2 states. So you see that the signal is stronger for the 2+, even if the wave function is more diffuse than in the neutron, in the 0+ case, where the signal is weaker, but the correlation between the neutrons in the wave function is stronger. And so what Casal did was try to see the asymptotic behavior of this wave function in momentum space. And so this result we have submitted to physical review letters, still under review. And the calculation, the spirit of the calculations is in the same spirit as Professor Wang Nazarevi's calculations for the 2-proton case. So here you see the red line is the result of this evolution of the wave function in momentum space for both states, and filtered by our setup. So of course the agreement is not perfect because this is not a fit. So Casal has not fitted the components of the wave function so that he can reproduce our result. This is just direct comparison without any fit, but you see that the main characteristics are well reproduced. So in both cases, we have a low energy neutron-neutron signal, and the signal is stronger for the 2+ case, like we see in the data. So this is a very strong improvement from the previous work on 2012 on Beijing 16. Now we have identified the 2 states, we have identified the different correlations, and we are able to compare with a microscopic model that will be able to learn to teach us about the properties, the decay properties of these systems. And with this, I move to the 3-neutron case. So we have seen that we can detect 2 neutrons and learn about the properties of these systems. Now let's move to the 3-neutron case. So first of all, we move into multi-neutron territory. So trineutrons, tetraneutrons, should those systems exist? And as I said, we wrote 2 years ago a review. So if those that are interested, you can check in the review the experimental part from myself and theoretical part from Carbonell. And here I will go very quickly through the theoretical part. So should they exist? So in the 1970s, some exact calculations were done for the 3-neutron system, and they all concluded that 3 neutrons. So this is from the work in 2002, at the same time that we published our first 4-neutron signal GANIL. It was the conclusion of this exact calculation saying that with the neutron-neutron interactions that we know, it was impossible to have a 3-neutron resonance. So they said that 3-neutron resonance close to the physical region will not exist. They didn't say they should not exist, they said they will not exist. Then in the early 2000s, Lazauskas, Carbonell, and Hiyama-san extended this work to the 4-neutron case, exact calculation of the 4-neutron case with the same conclusion. They concluded that this 4-neutron resonance will not exist. They even added some sophisticated 3-neutron forces with the same conclusion. But other kind of calculations using many body approximations, they said that maybe resonance could exist. However, in these recent years, 2019, 20, and so on, these authors of the exact calculations have quite demonstrated that the conclusions that many body approximations obtain are due to the method that they use and not to the physics. So they claim that multi-neutron resonance should not exist, and if they, in the conclusions of some of these papers, these ones claim that their conclusions are biased by the technique that they use. And others, like Del Tuba and Higgins, said that we could see peaks in the cross-section, but that they should not be assigned to resonances. So this was the overall conclusion. and on the theoretical part. Now, do 3-neutron systems exist in reality? And this experiment is a very beautiful one. So this picture has nothing to do with the experiment. It's just to make it beautiful, because this experiment in the 1980, they searched for a tri-neutron detecting gamma rays. So the reaction was a very simple one, conceptually. So pi minus on triton, and two-body reaction, gamma plus three neutrons. And they did not detect the neutrons. So in the 1980s, they used a photon spectrometer. The photon energy is very high because you have to compensate the pion mass. So it's about 120 MeV. This is the photon energy. And then here you have the bound, the 3-neutron limit. So if you see peaks to the right of this limit, this would mean that you have a bound tri-neutron. If you see peaks to the left, it would mean that you have a resonant tri-neutron. And what they measured was this spectrum, very high statistics and resolution, and the solid line is the calculations assuming no tri-neutron. So the conclusion was that they highly sensitive experiment saw no evidence for a tri-neutron. So this is the base experimental case. As I said, in almost at the same time, 1980, so in 1979, one of the papers that I quoted of the exact calculations of the 3-neutron case, they said this. So this is from the paper. So they say that the changes in the interaction are so huge that no one should try a very expensive experiment to measure a 3-neutron resonance. So they, as early as 1979, they suggested that people, experimentalists, should not even try to do an experiment to measure a 3-neutron resonance, because it was impossible and it would be a waste of money. So what I will show you here is not an experiment to search for the 3-neutron system. So this was an experiment to search for the 4-neutron system. So technically, we didn't waste our money in a 3-neutron search, because we wasted our money in a 4-neutron search. But in our experiment, we had also a 3-neutron channel as a byproduct. So this is what I will show you now. Here in this table, I have put together the latest 3 tetraneutron experiments at RIKEN. So in 2016, there was Shimura-san repeated his experiment that was published by Kisamori, his 4-neutron signal at RIKEN. He repeated the experiments in better conditions to see if they were able to confirm the weak signal. In 2017, Pascalis and collaborators proposed this technique. So the knockout of one alpha particle inside helium-8 with a proton, so PP alpha. And this is the result that has been published last year in Nature. And at the same time, we proposed the P2P reaction on helium-8 to try to produce hydrogen-7. And then hydrogen-7 could decay into a triton and a tetraneutron. This was a collaboration between LPC and RIKEN, so Sai-Hong Yang, that is now at Beijing University. So you see that the initial state was very similar of the 3 experiments. So very different techniques, but very similar experiment. Helium-8 beam in all cases. The energy was similar in all cases too. Here was a helium-4 target and a proton target. In this case, there was a double charge exchange of the target. Helium-4 went to tetraneutron, and helium-8 to beryllium-8, and they detected the 2 alpha particles. In this case, the proton knocks out the alpha particle, the proton and the alpha particle, and both are measured, and you reconstruct the 4 neutrons by missing mass. And in our case, the proton will kick 1 proton inside helium-8, both are measured, and then we have a triton and 4 neutrons, and all of them are measured. So why are we able to measure all the particles? Because of the cross-section. So the beam intensities are similar, but Shimura-san used a probe of the nanobarn level. Pascalis proposed this PP alpha knockout of the microbarn level, and we proposed this P2P reaction of the millibarn level. So you gain a factor 1,000 in number of events, and this allows us to detect also the neutrons, because in 2017 at RIKEN we had the nebula walls that I showed previously, and we also had the Neuland demonstrator. So with the combination of these detectors, we had a 4-neutron efficiency of the order of 1%. And with 1% efficiency, we could, on this millibarn cross-section, we could afford to detect all the particles. But before talking about the main channel, hydrogen-7, let's go to the helium-7 excitation that would decay in 3 neutrons. So you see that the reaction, instead of knocking out 1 proton from helium-8, we knock out 1 neutron. And then we have a final state with a helium-4 instead of a triton. Before going to our result, what do we know in the past experimentally from this helium-7 excited state? So this is an experiment at RIKEN in which this is without neutron detection. So you have P-D reaction on helium-8, proton target, and then you detect the deuteron, and you can tag. So the resolution of the fragment and the neutrons is very bad, but you can tag the channel. So in this case, you have the energy, the reconstructed energy of helium-7 when you detect a helium-6 here. And you see a peak very close to 0. This is the ground state of helium-7 that decays always to helium-6 plus neutron. Then they tag with helium-4. When you tag with helium-4, you see that the ground state disappears. So this ground state cannot decay to helium-4. Helium-4 is here. But you have another state in blue that was not present here. And this state is at about 3 MeV. This is the first excited state of helium-7. And this state decays to helium-4, not to helium-6. So there is no this decay. And the question was, because this was missing mass, so they measured the state, but they don't measure the decay. The question was, do we end up in helium-4 by direct emission of 3 neutrons, or do we go through the helium-6 2 plus state? So 1 neutron emission here, and then 2 neutron emission here. The interest for us is that if everything is sequential, we cannot form a trineutron. But if some branch is direct, then we can explore the possibility of the emission of a 3-neutron resonance. This is a view. So I have shown you already schemes of the schematic views. This is a picture of the setup. Here you have the beam detectors. Here you have the target detectors. Here you have dipole samurai, the focal plane detectors for the fragment, and the neutron detectors for the neutrons. And in this experiment, we had a liquid hydrogen target with a TPC in order to measure the proton trajectories, and with sodium iodide detectors to measure the proton energies. And this was the collaboration. So only part of the collaboration, because it was a very long campaign and everybody was tired. So here you have about 1/3 of the collaborators. Mainly you have people from France, from Germany, from China, and from Japan. And so these are preliminary results from the PhD of Cyril Lenat. So the primary beam in this case was oxygen 18. We produced helium-8 secondary beam, and then we want to remove one proton to make hydrogen 7 and explore the 4-neutron decay to the triton. But at the same time, we had also the 1 neutron knockout to populate helium 7, and then we can measure the decay to helium 4. And this is some observable. So this observable is the energy of helium 6 plus neutron. So we have the PPN reaction, and we measure 1 helium 6 and 1 neutron, and this is, you see the huge statistics. This is the helium 7 ground state that you see here. Then we measure helium 4 and 2 neutrons, and this is the helium 6 2 plus resonance that you see here. And then here you have the same helium 6 plus 1 neutron channel. So this time the scale is the energy of helium 7 excitation. So the ground starting from 0 here, you have the ground state here, and this is the 3 neutron channel. So now we have measured helium 4 and 3 neutrons in coincidence by invariant mass. So there is no missing mass here. We measure all the particles. And you see that starting from the 3 neutron threshold, you have this clear resonance that corresponds to the resonance that was observed by missing mass by Korsenikov some 20 years ago. So now we know exactly what is the resonance of the helium 7, and we can explore the decay because we have measured the neutrons. Do we have sequential decay or do we have direct 3-neutron emission? And in order to explore this, we have constructed here. So we have 3 neutron events, but we remove one of them, and we reconstruct helium 4 plus 2 neutrons. So you see here the signal associated with this helium 6 excited state. And what we do is we fit the data with a combination of 2 possibilities. The sequential decay here, 1 plus 2, and the direct decay here, 3. And you see that we have some direct component, so of the order of 20%. It's still very preliminary because we are analyzing this at LPC and at Beijing University in parallel. But it would mean that we have some direct 3-neutron emission component, and then we can wonder, since we have the momenta of the neutrons, is there any correlation between the neutrons and the alpha particle? So for example, here you have the cosine of the minimum angle between the alpha particle and each of the neutrons. So if you have these are simulations. If you have a 3-neutron resonance, then all the neutrons will be emitted back to back with respect to the alpha particle. And you see here what we should expect, a peak at very large angle. If, on the other hand, we have direct emission in 4-particle phase space, then you can have a very broad distribution of angles around 0 degrees, around 90 degrees, sorry. And then we plot all the data, and these are the data. So we can do this because we have measured the neutrons. If you use missing mass, you cannot go to this level, but now we can go to the correlations, and you see that it looks a lot like the phase space case. So it would be direct emission, but there would be no 3-neutron resonance. But this would be the first evidence of 3-neutron emission, but there is no prime neutron signal. And now, of course, so 4-body phase space is quite complicated because there are these are two extreme cases, but you have also things in between. So this is something we are exploring right now, but this is the first time that this 3-neutron decay has been measured. And then I move to the last part, so the 4-neutron case. I introduced already the setup. Is the same PhD from Cyril Lenin. Now we will have a look to the triton fragment in coincidence with 4 neutrons. So what is the hydrogen 7 ground state and what would be the signature of a tetraneutron? As I said, so this experiment was planned to measure this exactly, triton plus 4-neutron decay. So the idea with respect to the nature result, so in the nature result, they didn't measure the neutrons. So that's why also why they could publish earlier. But now they are not sure if their signal they see comes from a 4-neutron resonance or from the helium-8 initial state. In our case, we want to form hydrogen 7, and then this hydrogen 7 is the wall between the initial state and the final state. So once we have formed hydrogen 7, we forget about helium-8, and if hydrogen 7 contains a tetraneutron component, we should see it in the decay. This is why we are interested in emission, spontaneous emission of particles, of neutrons. So this is the same scheme I showed. So oxygen 18 primary beam, helium-8 secondary beam, 1 proton knockout, and we look for this decay. Just to be complete, in the collaboration, we have already measured 4 neutrons. So it was in a very recent Nature paper, oxygen 28. But from Kondo-san, Taitek, Kondo-san demonstrated that in oxygen 28, the decay is sequential. You have 2 neutron emission to oxygen 26 and 2 neutron emission to oxygen 24. So he already measured 4 neutrons, but he didn't measure 4 neutron decay. What we want to do here is try to measure 4 neutron decay for the first time, because there are no narrow, low energy intermediate states like oxygen 26 here. So this is the reaction. Just a reminder, we have helium-8, proton target. This proton is going to remove one of the protons, so we measure both. We are going to form this system, the triton with 4 neutrons, and then we have a 7-body final state. Of course, we measure the 2 protons, so without having a look to the decay of hydrogen 7, we can already reconstruct the energy of hydrogen 7. The problem is that the resolution would be quite low, so about few MeV. And this is in fact what was done in the past. So these are a collection of hydrogen 7 results, all from missing mass experiments. So you see here the first one from Kobayashi-san, HiMac. You see a broad structure close to threshold. Korchenikov also the broad structure close to threshold. You can see the energy scale, so it's huge. These were from GANIL, where they claimed, Camaño, in 2007, they claimed that the 4 events here were consistent with this red line input, so a very narrow, very low energy hydrogen 7 resonance. And these are from results from Dubna. Sometimes they saw nothing significant above threshold, just something broad. In more recent work, so this is 2021, you see the statistics are very low, but they associate every structure with a resonance. And so they claim that they have observed the ground state, first excited state, and so on. But the resolution is very bad. Again, you see here, each beam corresponds to 1 MeV. So what we want to do is measure also these particles and reconstruct hydrogen 7 for the first time using invariant mass. The gain, so we can go from few MeV resolution to 100 keV resolution. So the gain in resolution is huge. If we have very narrow state, then we will see it. And for this, of course, this is very beautiful to measure missing mass and invariant mass at the same time, but this means that we need a lot of detectors. So we need the minus liquid hydrogen target that will help us gain in luminosity. It's a very thick, it's 15 centimeters thick target. It's liquid hydrogen, so it's pure. There are no contaminants. We have a TPC to reconstruct the proton angle, so we have a very good resolution. With the Dali crystals that we add on around minus, we have the proton energy, so very good efficiency. And then with Samurai, we are going to detect the triton momentum, so good resolution. And with the combination of Nebula and Neuland, we can measure 3 and 4 neutrons with relatively high efficiency resolution, and we can access to the correlations. And these correlations are very important because, as I already introduced in the 3-neutron case, even if the energy of a resonance would be broad, or the width of a resonance would be broad, the kinematics are very different. 5-body phase space will populate the whole phase space, but a 2-body decay of a 4-neutron resonance would be very different in kinematics. So by measuring the neutrons and the triton, we can have access to these different kinematics. And then I come to the last part of this presentation. So I have shown you the 2-neutron results from beryllium-16 are definitive ones. So we have submitted already in the form that you have seen to physical regulators. The 3-neutron results that I have shown you for helium-7 are preliminary. The 4-neutron results from hydrogen-7 are very preliminary. So yeah, you can check them, but please don't take them as our definitive result. We are still working on them. So this is the first time that hydrogen-7 is reconstructed from the 5 decay particles. So this is the energy of the triton plus 1, 2, 3, and 4 neutrons. And this is what we get. So, of course, we didn't expect this from the previous experiments. Previous experiments were claiming very low energy resonances, very narrow. What we see is something very broad, relatively high energy. Of course, we have some fluctuations here that we are investigating. Do these correspond to resonances or not? Another thing we are investigating is the low energy response of our device. So this spectrum was obtained with a very strong crosstalk filter. So in order to detect 4 neutrons and be sure that these 4 neutrons are real, and we don't have 2 or 3 neutron detection that looks like 4, because some neutrons were detected twice, we have applied a very strong kinematic filter that eliminated events here. But we learned from Kondo-san and his oxygen-28 result that we can do a more sophisticated filter that will accept more events in this area. And this is explained in this NIM paper. So by using a more sophisticated filter that is not so strong at low energies, here you see the tail of the spectrum going to 0. And you see that there are no clear low energy resonance like GANIL claimed in 2007. So for the moment, we don't see very low energy, very narrow resonances. This is a first try. So what would happen if it fit the whole spectrum with one single resonance? It works, more or less. This is one resonance at 7 MeV with a 4 MeV width, so something very broad. This I'm not claiming that this is the truth, because we are still working on more complex fits. This is just a very simple fit. What happens if we use only one resonance, like the others did in the past? This is a bit more confusing, because here this dash histogram is an independent simulation of the 5 particles. So it's something like a non-correlated 5-particle emission, and it looks not exactly, but yeah, so it looks in part like the data. So it could be that these data do not correspond to just one resonance, and they have a resonant part and a non-resonant part. And this is also something we are investigating right now. But if we assume, for example, this hypothesis, let's consider that it's only one hydrogen 7 resonance, quite high in energy and quite broad. As I said, we have invariant mass, so we can measure the correlations, the partial correlations. So for example, we can remove the triton and measure the 4-neutron energy. So this is the 4-neutron energy, the energy of the 4-neutron system for the first time by invariant mass. So this is the result from the 4-neutron momenta. You see something that is peaked at about 2.5 MeV, so close to the result from the Nature paper. So does it mean that we have a 4-neutron resonance here? This is the angular correlation similar to the 3-neutron case. So this is the cosine of the minimum angle between the triton and each of the 4 neutrons. If you remember, a 4-neutron resonance would give us a peak at high angles. Phase space would give us something broad. So you see that the data, they look like a peak in the 4-neutron energy, but they don't look like something angular correlated. Now, of course, we can, by simulating this resonance, we can see what would be the projection of this resonance in these observables. And you see the red line here. This red line is the result of 5-body phase space of the decay of this broader structure. And you see that, yeah, so it explains the shape of the spectrum, but a bit shifted. And also, you see here what phase space would look like. It's also, there's a bit shift with respect to the data. As I said, this is a very simple extreme. So we assume only one resonance and only phase space. One small addition that we can easily do is add the neutron-neutron final state interaction between one neutron pair. So we take 2 neutrons from the 4, and we add the neutron-neutron final state interaction, and this gives the blue curve. So it's not right on the data, but you see that the shift goes in the direction of the data. So it could be that we are not measuring pure phase space, but that we have some 2-neutron correlations in the decay of hydrogen 7, and this would explain these two observables at once. So this is something we are still working on. So you see, measuring all the particles is better physics-wise, but it's also more complex. So it takes a lot of work to reach final conclusion. And just before I come to my conclusions, my general conclusions, for those that don't know, in 2022, Hiyama-san with Ratauskas and Carbonell published the first 5-body calculation of hydrogen 7. So this is a calculation of the 5-body problem, trying to find ground state of hydrogen 7. These are the configurations that they use in their 5 formalism, and also the Gaussian expansion method. And this is the main result of the paper. So this is the position of resonances. So this is these are the resonance pole. This is the energy the real part of the pole, so the energy of the resonance, and this is the imaginary part, which is related to the width. And they compare here with the previous hydrogen 5 work, in which they found the hydrogen 5 resonance at about 2.5, 2 MeV. And this is what they obtained for hydrogen 7. So with a similar three-body force, they obtained something in the vicinity of 8, 9 MeV and much broader. So this first 5-body calculation would be consistent with a broad high-energy hydrogen 7 resonance, but again, from the theoretical point of view, this is clear. From the experimental point of view, we are still working on it. So I hope I have been able to give you a quick overview of the things that we are doing at RIKEN right now. So it's not only that we detect neutrons. I show you how we make the beams, what are the detectors that we use, but also that by measuring 2, 3, and 4 neutron channels, we are addressing very different physics cases. So in the first case, the U16, we have demonstrated that there is no dineutron decay, as it was claimed in the past. And we have seen that with combining these measurements with three-body microscopic models, we can probe the 2-neutron wave function. In the 3-neutron case, we have shown that you can detect the 3-neutron emission, but of course, we have not observed a tri-neutron signal. And in the 4-neutron case, we don't see very clear low energy narrow states in hydrogen 7, but we are still working on the final conclusion. And depending on this, we will try to understand the correlations between the 4 neutrons that we have measured. And with this, I thank you for your attention.
Thank you very much for the very nice talk. So now is question time. And if anyone has questions or comments, please raise your hand or unmute yourself. So maybe let me first ask your question. So for those 2 neutron decay case in Brain 6, actually our group also did some preliminary calculations for that, and we found that it's actually quite interesting because when we include the deformations in this nuclei, I found that the small energy regions become more pronounced in this case. So I don't know if this might suppress the discrepancy between your experiment and theory, because as you know that the brain isotope is usually have a large deformations.
Yes. So as I said, this is we submitted last week. So we but what we wrote in this draft that we have submitted is that the fact that in these calculations the core is considered inert and spherical, this may explain the discrepancy. And of course, Casal, he would like, as a next step, he would like to include the deformation of the core, also in order to describe this variant 14.2+, because in this case the core is variant 12, which should be even more deformed. So we really believe that we hope that this data will encourage these calculations, and I will be very, very interested to see if you have already done these calculations. I will be very interested to see what is the effect.
Maybe if you are interested, we can send you our results for your consideration.
Yeah.
So
that would be very interesting for us.
Thank you. Yeah, and another thing, yes, it's quite interesting to see. Yes, you found that 3 neutron or 4 neutron direct decays in your case, because in proton case, even though we have some measurement for our collaborators has some measurement like the carbon 8, nitrogen 9, they found that those protons actually are strongly influenced by the pairing interactions. So usually they have some sequential decay by one proton or two protons, but not the 3 or 4 protons simultaneously. So it's quite interesting to see you got some results for that.
Yeah. So
and do you? Yeah, please go ahead.
In this case,
Mm-hmm.
so we only have one possible path. So it should be we need to be sure about this two-component fit, but at least we know that there are only 2 ingredients because there are no other states in this decay. But yeah, so most of the time when you have 3 particle decays, most of the time is sequential. And we would be very interested to confirm. This is why I said here about 20%, because we are still trying to confirm if this is the case.
And it is interesting to say that in this direct decay case, that the operation is quite similar to the phase space. So, do you have some comment why those final state interaction has little impact in this case, also in the 4 proton case, for neutron case?
Yeah. So maybe it is the parameter that we are using. So this was because this is just the minimum of the 3 angles. So yeah, I also expected that the sequential, because the data here are the whole data. So the whole data are most of the time sequential.
Yeah.
So I thought that going through helium going through helium 6 excited state would manifest somewhere here, but maybe this is not the best observable to see that. So this is something else we are working on. So first, try to disentangle if this is really a significant direct component, and then if we can check for other observables. This was the first one that we checked because in our proposal, we said that in the extreme case, in which you have a trineutron, you should have a peak here. And so this is easy to explain to the experimental pack. So if you demonstrate that you are able to see such a clear signal, then they think that the experiment should be done. But what we see is that there is no such strong signal. Now we have to go further in the observables that we use to see if we are sensitive to other things that are not related to the trineutron.
Yeah, I think this is a quite important way to show whether there is resistance for those trineutron or tetraneutron systems by the correlations. So as you mentioned, there is a debate on this tetraneutron signals, whether it is resonance. Right? Yes. So anyone else has questions? I think people are okay. So Chengwu, please go ahead.
Hello, Professor Marqués. I have a question regarding the hydrogen-7 issue. Yeah. In your result, it might looks like the hydrogen-7's energy is so high as 7 MeV in your work. So does it mean hydrogen-7 might be a sequential emission mode? Because it looks like a contrast to the published experimental results.
Yeah, so in all the other experiments, they don't even think about. So the main difference with oxygen-28 is that the hydrogen isotopes, so 4 and 6, are very broad. Hydrogen-5 has a resonance at about 2 MeV, a bit narrower. So our expectation was that if we had a if we had hydrogen 7 somewhere here, then there would be no intermediate states. So hydrogen 4 and 6 are above 2 MeV. Hydrogen 5 is at about 2 MeV. So if hydrogen 7 was somewhere here, the only decay possible was the direct decay of the 4 neutrons. Now we don't see states here. So this makes us think again about it. So in the proposal, the only thing that we knew was that. And the main result that is quoted in hydrogen 7 is this one. So in the proposal, we said that we were able to see if we confirm this very low energy state, we would be able to measure the 4-neutron decay. But now what we see is something here. And if something is here, of course, you can decay through here, through hydrogen 5, as you said. So we could have here the decay through hydrogen 5. So this is something that we are going to explore, but there are two separate things. So in this slide, if you trace a line in the middle, on the left, you have the object that you have formed. So we have formed hydrogen 7. And we should be able to describe this hydrogen 7 energy independently of the decay mode. So on the left, you have the starting point, what you created. On the right, you have the decay consequences. So what you say about the passage through hydrogen 5, we should explore in this part here. So as Professor Wang said, if we have a sequential decay, 2 neutrons and then 2 other neutrons, we should see what is the manifestation of this decay here in the angular correlation. But at the present point, we are still on the left. So we are trying to see what is the best description of the hydrogen 7. Of course, if you have only one state, it's easier because then you have only one starting point. But if we find that we have several resonances on top of some non-resonant background, then it is much more complex because you have a lot of degrees of freedom in the decay. So maybe if you have a very complex input, we will not be able to see clearly the sequential decay. But if the input is easier, then we may see the manifestation of sequential decay. So this is part of the problem right now. We need to be sure of the input before trying to see the decay observables.
Okay, thank you, Professor.
So anyone else has a question?
I didn't mention, but now there are new experiments that have been proposed at RIKEN. There is one wanting to measure this and also the decay of helium-8 by invariant-mass. So the next experiments at RIKEN will have the same data quality as this one for other systems, not only hydrogen 7. So the things that we are exploring now I think will be used in the analysis of the next experiments that want to be able to distinguish between the effects of the initial structure and the effects of the possible resonances in the final state.
Yes. So if there's no any other questions, so let's thank Professor Marqués again. So for this nice talk, and welcome to Fudan anytime. If you want to visit us, you are definitely welcome.
Yeah, I hope.
Thank you very much.
Thank you very much.
Okay, so the seminar is over here. See you next time.
See you.